Jupiter is massive. Not big for a planet. Massive. Fundamentally, cosmically massive. If you took all the other planets in the solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and every asteroid, comet, and moon, and combined them into one object, Jupiter would still be more than twice as massive. Jupiter is 318 times more massive than Earth. It could fit 1,300 Earths inside its volume. From space, Jupiter appears as a series of alternating light and dark bands, zones and belts of clouds, swirling at different speeds and directions. This banded structure is driven by Jupiter's rapid rotation. Jupiter spins once every 10 hours. Despite being 11 times wider than Earth, it completes a day in less than half the time. This rapid rotation creates powerful atmospheric dynamics. And then there is the Great Red Spot, a storm larger than Earth that has been raging for at least 400 years, possibly much longer. When astronomers first observed the Great Red Spot in the 1600s, they assumed it was a temporary feature. Storms come and go, right? Wrong. The Great Red Spot has been continuously observed for over 4 centuries. It's a permanent feature of Jupiter's atmosphere, an anticyclonic storm with winds exceeding 400 miles per hour. Although the spot has been shrinking. In the 1800s, it was large enough to fit 3 Earths across. Now it's down to 1 Earth. Scientists aren't sure if it will eventually disappear or stabilize at a smaller size. But the Great Red Spot isn't alone. Jupiter has dozens of storms, including Oval BA, nicknamed Red Spot Jr., various white ovals, and smaller cyclonic and anticyclonic systems. And below that, well, below that is where things get weird. Let's imagine descending into Jupiter in a magical indestructible probe. What would we experience? At 0 miles, cloud tops, temperature minus 150 degrees Celsius, pressure 1 atmosphere same as Earth's surface, ammonia ice crystals swirling around us, sunlight penetrating through the thin upper haze. This is as nice as Jupiter gets. At 30 miles deep, temperature minus 50 degrees Celsius, pressure 5 atmospheres. We've entered the water cloud layer. Still cold, but warming up. Visibility would be near 0 thick clouds surrounding us, lightning flashing in the distance. Yes, Jupiter has lightning far more powerful than Earth's. At 60 miles deep, temperature 0 degrees Celsius, the freezing point of water. Pressure 10 atmospheres. We're now below the visible clouds, entering a region of hydrogen and helium gas. It's getting darker. The sunlight can't penetrate this far. We're descending into darkness. At 600 miles deep, temperature 150 degrees Celsius, pressure 2,000 atmospheres, 2,000 times Earth sea level pressure. The hydrogen gas around us is getting denser and denser. It no longer behaves like a gas. It's becoming more fluid-like. We're entering a transition zone. At 1,200 miles deep, temperature 20 degrees Celsius hot, enough to melt iron. Pressure 50,000 atmospheres. The hydrogen is now so compressed, it's become liquid. Not liquid like water liquid metallic hydrogen, where the pressure is so intense that electrons are squeezed off hydrogen atoms, creating a conductive metallic fluid. And this is where Jupiter gets truly alien. Below about 1,200 miles depth, Jupiter is made of liquid metallic hydrogen. This is a state of matter that doesn't exist naturally on Earth. We can barely create it in laboratories for microseconds before it reverts to normal hydrogen. But in Jupiter's interior, this metallic hydrogen layer extends for 40,000 miles, nearly the diameter of Neptune. Liquid metallic hydrogen is electrically conductive. As Jupiter rotates rapidly, this conductive fluid generates the most powerful planetary magnetic field in the solar system, 20,000 times stronger than Earth's. Jupiter's magnetosphere extends millions of miles into space, creating an enormous bubble that traps charged particles. This is what makes Jupiter's radiation belt so deadly. If Earth's magnetosphere is a shield, Jupiter's is a fortress. At 10,000 miles deep, temperature 10 degrees Celsius hot enough to vaporize any known material. Pressure millions of atmospheres. The metallic hydrogen around us is denser than liquid lead. This isn't a gas giant anymore. It's a liquid metallic hydrogen planet with a thin gaseous envelope. At these depths, the pressure and temperature are so extreme that chemistry, as we know, doesn't apply. Atoms are crushed together, electrons flow freely, and the distinction between gas and liquid and solid becomes meaningless. At the core, temperature possibly 25 degrees Celsius hotter than the surface of the Sun. Pressure tens of millions of atmospheres. Jupiter's core is probably made of rock and ice materials left over from Jupiter's formation. But at these temperatures and pressures, rock and ice don't mean what they mean on Earth. Everything is so compressed and hot that it exists in exotic, high-pressure phases. The core might be 15 to 20 times Earth's mass larger than Earth itself, but compressed to a fraction of the size. So when we say Jupiter is a gas giant, that's deeply misleading. Only the outermost 1,000 miles is actually gas. The vast majority of Jupiter is liquid metallic hydrogen, a substance so exotic we barely understand it. Jupiter is more accurately a liquid metallic hydrogen giant with a thin gaseous envelope. But that doesn't roll off the tongue as easily. Jupiter has at least 95 known moons. We've already talked about Io and Europa. Ganymede, the largest, is bigger than Mercury and has its own magnetic field, the only moon in the solar system with one. Callisto is heavily cratered and ancient, geologically dead for billions of years. But the outer moons are even stranger, small, irregular objects in retrograde orbits, probably captured asteroids. Some orbit Jupiter in the wrong direction, taking decades to complete one orbit. Jupiter is essentially a miniature solar system, with a family of worlds orbiting it. And yes, Jupiter has rings. Faint, dusty rings created by material knocked off its small inner moons by meteorite impacts. They're nothing like Saturn's spectacular rings, but they exist invisible to Earth-based telescopes, discovered only when Voyager 1 looked back at Jupiter, backlit by the Sun. Jupiter's auroras are the most powerful in the solar system, far brighter and larger than Earth's. They're powered by material from Io's volcanoes, charged particles trapped in Jupiter's magnetosphere, and the planet's own rotation. The auroral emissions are mostly ultraviolet, but they extend into X-rays. Jupiter's auroras are literally glowing in X-rays, created by energies we can barely comprehend. NASA's Juno mission, which arrived at Jupiter in 2016, has revolutionized our understanding of the planet. It flies in a polar orbit, diving close to Jupiter's cloud tops every 53 days. Juno discovered that Jupiter's atmospheric weather patterns extend far deeper than expected, thousands of miles into the interior. The Great Red Spot's roots go down at least 200 miles, possibly much farther. Juno also mapped Jupiter's gravitational field with incredible precision, revealing that the core might be partially dissolved or fuzzy, not a sharp boundary between core and envelope, but a gradual transition. One of Juno's biggest surprises: Jupiter has way more water than expected. The concentration of water in Jupiter's atmosphere is 3 times higher than on the Sun. This suggests Jupiter formed farther from the Sun than its current position, in a region where water ice was abundant and migrated inward. It's evidence for the Grand Tack hypothesis. The idea that Jupiter's orbit shifted dramatically during the solar system's early history. Jupiter radiates more energy than it receives from the Sun. It emits 1.7 times the energy it absorbs, meaning it has an internal heat source. That heat comes from two sources: leftover heat from Jupiter's formation 4.5 billion years ago, and helium rain. Wait, helium rain? Saturn is less massive, less dense, and has weather patterns that make Jupiter's storms look calm by comparison. Oh, and Saturn has those rings. Let's talk about those rings. From Earth, Saturn is the most recognizable planet, those magnificent rings visible through even a modest telescope. But here's something most people don't know. Saturn's rings shouldn't exist. The rings are incredibly thin, less than 100 meters thick in most places, despite being over 280,000 kilometers wide. If you built a scale model where the rings were as thin as paper, they'd be a kilometer across. They're made almost entirely of water ice chunks, ranging from dust-sized particles to house-sized boulders, all orbiting Saturn in a vast, flat disk. And they're young, really young. For decades, scientists assumed Saturn's rings formed with the planet 4.5 billion years ago. But data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, tells a different story. The rings are probably less than 100 million years, old possibly as young as 10 million years. How do we know? By measuring how polluted the rings are. Space is full of micrometeorites, tiny particles that constantly rain down on everything. These particles are rocky and organic, unlike the pure water ice of Saturn's rings. If Saturn's rings were billions of years old, they should be heavily contaminated with this dark material, appearing grayish or brownish. Instead, they're brilliant white, nearly pure ice. This means the rings formed relatively recently, and they're still relatively clean. So, where did the rings come from? A leading theory: a moon ventured too close to Saturn within the Roche limit, the distance where Saturn's tidal forces are stronger than the moon's own gravity. The moon was torn apart, and its icy material formed the rings. Alternatively, a large moon might have been struck by a comet or asteroid, shattering it into the rings we see today. Either way, the rings are the remains of a destroyed moon. The rings aren't uniform. They're divided into distinct sections separated by gaps. The most famous gap is the Cassini division, a 4,700-kilometer wide gap between the A ring and B ring. This gap is created by gravitational resonances with Saturn's moons, particularly Mimas. Whenever a ring particle enters an orbit that resonates with Mimas's orbit, Mimas's gravity perturbs it, eventually clearing that orbital zone. Over millions of years, this creates the gaps we see. Some gaps contain small shepherd moons, tiny moons that orbit within the rings, using their gravity to maintain sharp edges on the ring boundaries. Pan and Daphnis are examples moons just 20 to 30 kilometers across, but their presence creates wave patterns and gaps in the rings. They're like cosmic lawnmowers, clearing paths as they orbit. Saturn's rings are dying. The magnetic field interaction between Saturn and the rings creates a phenomenon called ring rain charged water ice particles spiraling down Saturn's magnetic field lines into the planet's atmosphere. Cassini measured this ring rain and calculated that Saturn is losing about 1 Olympic swimming pool's worth of water from the rings every half hour. At this rate, the rings will be gone in 300 million years, a blink of an eye in cosmic terms. This means that billions of years from now, Saturn will be a ringless planet, like a less interesting Jupiter. Future astronomers studying our solar system will have no idea Saturn once had spectacular rings. We're living in a special time, a narrow window in solar system history when Saturn has rings. Let's descend into Saturn itself. Like Jupiter, Saturn is a gas giant, or more accurately, a liquid metallic hydrogen giant with a gaseous envelope. But Saturn is different from Jupiter in key ways. First, there's the hexagon. Saturn's north pole has a persistent hexagonal cloud pattern, a 6-sided jet stream, each side about 9,000 miles long, traveling at 200 miles per hour. This hexagon has been observed since the 1980s, and it's still there, unchanged. We don't fully understand how it forms or why it's so stable. It's like nature decided to draw a giant geometric shape on a planet, just to mess with us. The South Pole has a different feature, a hurricane-like vortex with a clearly defined eye, much like terrestrial hurricanes. But this storm is 5,000 miles across, and unlike Earth's hurricanes, it doesn't move. It's locked to the pole, spinning in place. Saturn is the least dense planet in the solar system. Its average density is 0.687 grams per cubic centimeter less dense than water. This leads to the famous factoid: if you could find a bathtub big enough, Saturn would float. Of course, such a bathtub would need to be 750,000 miles across and contain quintillions of gallons of water, but theoretically, Saturn would float. Saturn's atmosphere is about 96% hydrogen and 3% helium, with traces of methane, ammonia, and other compounds. It's similar to Jupiter, but with less helium likely, because helium is raining out of the atmosphere into the interior, same as Jupiter. The cloud layers are similar to Jupiter's. Ammonia ice clouds at the top, ammonium hydrosulfide clouds below, water ice clouds deeper still. But Saturn's winds are even faster than Jupiter's. Wind speeds at the equator reach 1,100 miles per hour, 4 times faster than Jupiter's strongest winds. These super-rotating winds are driven by Saturn's internal heat and rapid rotation. A Saturn day is only 10.7 hours. Below the visible atmosphere, Saturn transitions to liquid metallic hydrogen, same as Jupiter. But because Saturn is less massive, this transition happens at shallower depths around 18,000 miles below the cloud tops, compared to Jupiter's 1,200 miles. Saturn's interior is similar in structure to Jupiter's, but less extreme in every way: lower pressures, lower temperatures, smaller core. Saturn's magnetic field is weaker than Jupiter's, but still 600 times stronger than Earth's. Field is remarkably symmetric, almost perfectly aligned with Saturn's rotation axis, unlike most planets whose magnetic fields are tilted. This symmetry is unusual and not fully understood. Saturn has 146 known moons more than any other planet. We've talked about Triton and Enceladus, but there are many others. Iapetus has a two-tone appearance. One hemisphere is bright white ice, the other is covered in dark reddish material, possibly from another moon. It also has a massive equatorial ridge, giving it a walnut-like appearance. Mimas looks like the Death Star from Star Wars because of a massive impact crater that nearly destroyed the moon. Hyperion is irregularly shaped and tumbles chaotically in its orbit. It doesn't have a stable rotation axis. Many of Saturn's moons interact with the rings, either maintaining gaps, creating waves, or generating new ring material. The system is dynamic, constantly evolving. Some small moons might be formed from ring material that accreted together. Others might be captured objects. Saturn's system is a complex gravitational ballet. Cassini's final act was diving into Saturn's atmosphere in 2017. Before running out of fuel, the spacecraft made 22 dives between Saturn and its rings, the grand finale, collecting unprecedented data about the planet and rings. Then it plunged into Saturn's atmosphere, transmitting data until it was destroyed by the heat and pressure. It was a fitting end for a mission that revolutionized our understanding of Saturn. But Saturn and Jupiter, for all their strangeness, are relatively close to the Sun and warm by gas giant standards. Out beyond Saturn's orbit lies the true realm of cold and darkness, the ice giants. And the most extreme of these is Neptune, where the wind screams at supersonic speeds and the interior rains diamonds. Neptune is 2.8 billion miles from the Sun, 30 times farther than Earth. Sunlight reaching. Neptune is 900 times dimmer than on Earth. You'd think Neptune would be a frozen, quiet world. Instead, it has the fastest winds in the solar system. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit, it discovered winds exceeding 1,200 miles per hour. That's faster than the speed of sound on Earth. Supersonic winds, howling across a planet that receives almost no energy from the Sun. Voyager also discovered the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot. But by the time the Hubble Space Telescope observed Neptune 5 years later, the Great Dark Spot had vanished. In its place, a different Great Dark Spot on the opposite hemisphere. Neptune's storms form and dissipate on timescales of years, unlike Jupiter's century-spanning storms. Neptune's atmosphere is far more dynamic and chaotic. Neptune's brilliant blue color comes from methane in its atmosphere. Methane absorbs red light and reflects blue, giving Neptune its striking azure appearance. But here's the weird part. Uranus also has methane in its atmosphere at similar concentrations. Yet Uranus appears pale cyan, not deep blue. Something else in Neptune's atmosphere, possibly an unknown compound, makes it bluer. After 35 years, we still don't fully understand why Neptune is so blue. Neptune radiates 2.6 times more energy than it receives from the Sun. It has a powerful internal heat source, far stronger than Uranus, which barely radiates any excess heat. This internal heat drives Neptune's extreme weather. But the source of this heat is debated. It might be leftover heat from formation, or it might involve something more exotic happening in Neptune's interior. And that brings us to the diamonds. Deep in Neptune's interior, at pressures around 200 gigapascals, 2 million atmospheres, and temperatures around 5,000 Kelvin, methane molecules break apart. The carbon atoms then crystallize under the extreme pressure into diamonds. Scientists estimate that Neptune might have a layer where diamonds form and then rain downward through the mantle, accumulating in a layer around the core. We're not talking about small diamonds. We're talking about diamonds the size of hailstones, possibly even larger, sinking slowly through Neptune's interior. This isn't pure speculation. Scientists have recreated the conditions of Neptune's interior in laboratories using diamond anvil cells and powerful lasers. And they've successfully created diamonds from methane under Neptune-like conditions. The experiments confirmed, yes, it should rain diamonds inside Neptune. And Uranus, which has a similar interior, probably has the same phenomenon. Neptune's magnetic field is bizarre. It's tilted 47 degrees from its rotation axis and offset from the planet's center by more than half a radius. This creates a lopsided, tumbling magnetosphere that wobbles as Neptune rotates. Charged particles trapped in the magnetic field are swung around wildly, creating complex auroral displays and intense radiation belts in unexpected places. Neptune's largest moon, Triton, is equally strange. It orbits backwards retrograde, suggesting it was captured from the Kuiper belt rather than forming with Neptune. Triton is geologically active, with nitrogen geysers erupting from its surface and depositing dark material across its icy plains. It's one of the coldest surfaces in the solar system at minus 391 degrees Fahrenheit, yet it's not geologically dead. Triton is also spiraling slowly inward toward Neptune. In about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system that will eventually rain down onto Neptune's atmosphere. Neptune is so far from the Sun that from its cloud tops, the Sun appears only slightly brighter than Venus appears from Earth. It's a dim, distant point of light. Yet despite the cold and darkness, Neptune is one of the most active, dynamic, and violent worlds in the solar system. It's a reminder that distance from the Sun doesn't mean quiet. Neptune is screaming across the cosmos, its atmosphere howling with supersonic winds, its interior raining diamonds, its storms forming and dissipating in chaotic patterns. And we visited it exactly once, for a few hours in 1989. Neptune is extreme, but it's not the most extreme world we've found. Because when you go closer to the Sun or farther into the depths of space, you find conditions that make Neptune look almost hospitable. Let's visit the hellscapes at the edges of our solar system. Mercury is the closest planet to the Sun, orbiting at just 36 million miles on average. And because of that proximity, you'd expect it to be the hottest planet. It is during the day. But at night, Mercury gets cold, really cold. During Mercury's 2-month-long day, surface temperatures reach 800 degrees Fahrenheit hot, enough to melt lead and zinc. But during the equally long night, with no atmosphere to retain heat, temperatures plunge to minus 290 degrees Fahrenheit. That's a temperature swing of over 1,000 degrees Fahrenheit between day and night, the largest temperature range of any planet in the solar system. And Mercury's day-night cycle is bizarre. Mercury rotates 3 times for every 2 orbits around the Sun. This 3-to-2 spin-orbit resonance creates a strange effect. From certain locations on Mercury's surface, the Sun would appear to rise, pause, reverse direction, and then set again, all in the same day. This happens because Mercury's orbital speed changes as it moves along its elliptical orbit. When it's closest to the Sun, it's moving faster in its orbit than it's rotating. This makes the Sun appear to move backwards in Mercury's sky before resuming its forward motion. It's a solar illusion created by orbital mechanics. Despite Mercury's proximity to the Sun, it has ice. At Mercury's poles, there are deep craters whose floors are in permanent shadow. The Sun never shines into these craters, and temperatures there remain below minus 280 degrees Fahrenheit year-round. Radar observations have detected bright, reflective deposits in these craters, almost certainly water ice, possibly mixed with frozen organic compounds. How did ice get to Mercury? Probably from comet impacts. Comets are essentially dirty snowballs, and when they strike Mercury, some of their water ice can become trapped in these permanently shadowed craters where it never melts. So Mercury has the hottest daytime temperatures and some of the coldest permanently shadowed regions in the solar system, existing side by side. Mercury is the densest planet after Earth. It has an enormous iron core that makes up 85% of the planet's radius, far larger proportionally than any other planet's core. This massive core creates a magnetic field weak by planetary standards, but unexpected for such a small world. Why is Mercury's core so large? One theory: Mercury formed farther from the Sun and was then struck by a massive impactor that blasted away much of its rocky mantle, leaving the iron core exposed. This would explain why Mercury is so dense and metal-rich. Mercury's surface is covered in scarps, massive cliffs formed as the planet cooled and contracted. Some of these scarps are hundreds of miles long and 1 to 2 miles high. The entire planet shrank as its core cooled, wrinkling the crust like a dried apple. These scarps are evidence that Mercury is still geologically active, at least in terms of cooling and contracting. Mercury's largest feature is the Caloris Basin, a 960-mile-wide impact crater created by a massive asteroid or comet impact early in the solar system's history. The impact was so violent that it created shockwaves that traveled through Mercury's interior and formed weird terrain on the exact opposite side of the planet jumbled. Chaotic landscape created by the seismic waves converging. Mercury's heavily cratered surface is a time capsule, a record of the early solar system as violent bombardment period. While Earth's plate tectonics and erosion have erased most evidence of ancient impacts, Mercury has preserved them. NASA's Messenger mission, 2011 to 2015, orbited Mercury and mapped its surface, magnetic field, and composition. It discovered the ice deposits, the weird day-night cycle effects, and evidence of past volcanic activity. Mercury turned out to be far more geologically complex and interesting than expected for such a small, airless world. But if Mercury is the extreme of heat and cold combined, let's just talk about a world that's just extreme cold one of the coldest surfaces in the solar system. We mentioned it briefly earlier. Now let's give it the attention it deserves. Triton, Neptune's captured moon, and the closest thing to a frozen alien world you'll find. Triton orbits Neptune in the wrong direction. While Neptune rotates counterclockwise, Triton orbits clockwise, a retrograde orbit that immediately tells us Triton didn't form with Neptune. It was captured, probably from the Kuiper belt. At minus 391 degrees Fahrenheit, Triton's surface is one of the coldest in the solar system, only about 68 degrees above absolute zero. At that temperature, nitrogen freezes solid, methane freezes solid, even carbon monoxide freezes solid. And yet, Triton is geologically active. Voyager 2 discovered something incredible when it flew past Triton in 1989. Geysers, plumes of nitrogen gas, and dark organic particles erupting from Triton's surface, reaching heights of 5 miles, then being blown downwind for up to 90 miles before settling back to the surface as dark streaks. At minus 391 degrees, geysers are erupting. How is this possible? Scientists think sunlight, even the dim sunlight reaching Neptune estims penetrates Triton's transparent nitrogen ice crust and heats the darker material below. This creates pockets of pressurized nitrogen gas that eventually break through the ice in explosive vents. It's like a cryogenic version of geothermal activity, powered by sunlight rather than internal heat. Triton's surface has bizarre, cantaloupe terrain, a landscape of pitted, dimpled regions that looks exactly like the skin of a cantaloupe. These features might be formed by Diapir's warmer ice rising through colder ice, similar to lava lamps. Or they might be collapse features from subsurface melting. Either way, they're unique in the solar system. Other regions show smooth plains of frozen nitrogen and methane, punctuated by ridges and valleys. Very few impact craters, suggesting the surface has been resurfaced relatively recently, within the last 10 to 100 million years. Triton's retrograde orbit means it's spiraling inward toward Neptune. As it does, tidal forces are circularizing its orbit and generating heat in Triton's interior. Eventually, billions of years from now, Triton will be torn apart by Neptune's gravity. But for now, it has enough internal heat to drive geological activity, even at temperatures that should freeze everything solid. Triton has an extremely thin atmosphere, about 70,000 times thinner than Earth's. It's mostly nitrogen with traces of methane and carbon monoxide. This atmosphere is so thin, it barely qualifies as an atmosphere. Yet it's thick enough to have winds that carry geyser material across the surface, creating those dark streaks. Triton's retrograde orbit is a death sentence on cosmic timescales. Every orbit, it loses energy to tidal friction. That energy loss causes the orbit to decay to slowly spiral inward. In about 3.6 billion years, Triton will cross Neptune's Roche limit. At that point, Neptune's tidal forces will be stronger than Triton's own gravity, and the moon will be torn apart. Mercury is the closest planet to the Sun, orbiting at just 36 million miles on average. And because of that proximity, you'd expect it to be the hottest planet. it is during the day. But at night, Mercury gets cold, really cold. During Mercury's 2-month-long day, surface temperatures reach 800 degrees Fahrenheit hot, enough to melt lead and zinc. But during the equally long night, with no atmosphere to retain heat, temperatures plunge to minus 290 degrees Fahrenheit. That's a temperature swing of over 1,000 degrees Fahrenheit between day and night, the largest temperature range of any planet in the solar system. And Mercury's day-night cycle is bizarre. Mercury rotates 3 times for every 2 orbits around the Sun. This 3-to-2 spin-orbit resonance creates a strange effect. From certain locations on Mercury's surface, the Sun would appear to rise, pause, reverse direction, and then set again, all in the same day. This happens because Mercury's orbital speed changes as it moves along its elliptical orbit. When it's closest to the Sun, it's moving faster in its orbit than it's rotating. This makes the Sun appear to move backwards in Mercury's sky before resuming its forward motion. It's a solar illusion created by orbital mechanics. Despite Mercury's proximity to the Sun, it has ice. At Mercury's poles, there are deep craters whose floors are in permanent shadow. The Sun never shines into these craters, and temperatures there remain below minus 280 degrees Fahrenheit year-round. Radar observations have detected bright, reflective deposits in these craters, almost certainly water ice, possibly mixed with frozen organic compounds. How did ice get to Mercury? Probably from comet impacts. Comets are essentially dirty snowballs, and when they strike Mercury, some of their water ice can become trapped in these permanently shadowed craters where it never melts. So Mercury has the hottest daytime temperatures and some of the coldest permanently shadowed regions in the solar system, existing side by side. Mercury is the densest planet after Earth. It has an enormous iron core that makes up 85% of the planet's radius, far larger proportionally than any other planet's core. This massive core creates a magnetic field weak by planetary standards, but unexpected for such a small world. Why is Mercury's core so large? One theory: Mercury formed farther from the Sun and was then struck by a massive impactor that blasted away much of its rocky mantle, leaving the iron core exposed. This would explain why Mercury is so dense and metal-rich. Mercury's surface is covered in scarps, massive cliffs, formed as the planet cooled and contracted. Some of these scarps are hundreds of miles long and 1 to 2 miles high. The entire planet shrank as its core cooled, wrinkling the crust like a dried apple. These scarps are evidence that Mercury is still geologically active, at least in terms of cooling and contracting. Mercury's largest feature is the Caloris Basin, a 960-mile-wide impact crater created by a massive asteroid or comet impact early in the solar system's history. The impact was so violent that it created shockwaves that traveled through Mercury's interior and formed weird terrain on the exact opposite side of the planet jumbled, chaotic landscape created by the seismic waves converging. Mercury's heavily cratered surface is a time capsule, a record of the early solar system's violent bombardment period. While Earth's plate tectonics and erosion have erased most evidence of ancient impacts, Mercury has preserved them. NASA's Messenger mission, 2011 to 2015, orbited Mercury and mapped its surface, magnetic field, and composition. It discovered the ice deposits, the weird day-night cycle effects, and evidence of past volcanic activity. Mercury turned out to be far more geologically complex and interesting than expected for such a small, airless world. But if Mercury is the extreme of heat and cold combined, let us talk about a world that's just extreme cold, one of the coldest surfaces in the solar system. We mentioned it briefly earlier. Now let's give it the attention it deserves. Triton, Neptune's captured moon, and the closest thing to a frozen alien world you'll find. Between Mars and Jupiter lies the asteroid belt, a region of space containing millions of rocky objects ranging from dust-sized particles to dwarf planets. Ceres at 590 miles in diameter. Popular culture depicts the asteroid belt as a dense field of rocks that spacecraft must carefully navigate. The reality? Space in the asteroid belt is mostly empty. You could fly through it blindfolded and have almost zero chance of hitting anything. The average distance between asteroids in the belt is about 600,000 miles. That's more than twice the distance between Earth and the Moon. The asteroid belt is sparse, not crowded. And despite containing millions of objects, the entire asteroid belt has less mass than Earth's moon. If you combined every asteroid into a single body, you'd get something smaller than Pluto. The asteroid belt is a failed planet material that never coalesced because of Jupiter's gravitational interference. The largest object in the asteroid belt is Ceres large enough to be spherical, which earned it dwarf planet status in 2006. Ceres is fascinating. It's about 25% water, by mass more water than all of Earth's freshwater combined. That water exists as ice beneath a rocky crust, possibly forming a subsurface ocean. NASA's Dawn mission, 2015 to 2018, orbited Ceres and discovered bright spots in a crater deposits of sodium carbonate, a type of salt left behind by evaporating brines. This means Ceres has or had liquid water near its surface. Water mixed with salts percolated up from below, filled the crater, and evaporated, leaving behind these brilliant white deposits. Ceres also has Ahuna Mons, a 13,000-foot-tall mountain that appears to be a cryovolcano. Not a volcano erupting lava, but one erupting salty water and ice. This mountain is relatively young, maybe only 200 million years old, suggesting Ceres is still geologically active. The second largest asteroid, Vesta, is completely different. It's a differentiated body with an iron core, rocky mantle, and basaltic crust, essentially a planetary embryo. Vesta began forming into a proper planet 4.5 billion years ago, but Jupiter's gravity prevented it from accreting more material. It's a frozen moment in planetary formation. Vesta has one of the largest impact craters in the solar system relative to the body's size, Rhea Silvia, a crater 300 miles wide on a 326-mile diameter asteroid. This impact nearly destroyed Vesta. It excavated material from deep in Vesta's interior, exposing the mantle. Debris from this impact was scattered throughout the asteroid belt, and some pieces have fallen to Earth as meteorites. When scientists analyzed certain meteorites called HEDs, Howardites, Eucrites, Diogenites, they found the composition matched Vesta's surface. We've literally held pieces of Vesta in our hands before ever visiting it. The asteroid belt contains families, groups of asteroids with similar orbits and compositions, indicating they came from a single parent body that was shattered by a collision. The Flora family, Vesta family, Eos family each represents a catastrophic collision that destroyed a large asteroid and created a cloud of fragments that still orbit together. Asteroids come in different types based on composition. C-type, carbonaceous. Dark, carbon-rich asteroids that make up 75% of the belt. S-type, silicaceous. Rocky, silicate-rich asteroids, common in the inner belt. N-type, metallic, iron-nickel asteroids. Possibly exposed cores of differentiated bodies. V-type, basaltic asteroids, fragments of Vesta. Each type tells a story about solar system formation and evolution. The asteroid belt has Kirkwood gaps, regions where asteroids are scarce because of orbital resonances with Jupiter. Any asteroid in a 3-to-1 or 2-to-1 resonance with Jupiter gets perturbed over millions of years, eventually being ejected from that orbital zone. This creates empty bands in the belt. Jupiter shaped the asteroid belt through gravitational influence alone, without ever physically interacting with the asteroids. Many asteroids are oddly shaped because they're too small for gravity to pull them into spheres. They're rubble piles, collections of smaller fragments barely held together by gravity. Itokawa, visited by Japan's Hayabusa spacecraft, looks like a peanut. Its two lobes connected by a narrow neck spinning once every 12 hours. If you stood on Itokoa, you'd weigh about 1/100,000th of your Earth weight. You could jump and escape its gravity entirely. About 15% of asteroids are binary systems, two asteroids orbiting each other. Some even have multiple companions, forming miniature solar systems. Ida has a moon called Dactyl. Pluto, now classified as a dwarf planet, has 5 moons. Even tiny asteroids can have companions. Beyond the main belt, there are Trojan asteroids objects that share Jupiter's orbit, sitting at stable Lagrange points 60 degrees ahead of and behind Jupiter. These Trojans are distinct from belt asteroids, possibly captured from the outer solar system during the solar system's early migration period. Some asteroids have orbits that cross Earth's orbit-near-Earth asteroids, NEAs. These are the potentially hazardous objects that could someday impact Earth. NASA tracks over 30,000 NEAs, and the catalog grows daily. Most are small, but some are large enough to cause regional or global devastation if they hit. Asteroids contain vast mineral wealth. M-type asteroids are essentially solid metal iron, nickel, platinum group metals. A single large M-type asteroid could contain more platinum than has been mined in all of human history. This has led to proposals for asteroid mining, sending robotic spacecraft to extract valuable materials and return them to Earth or use them in space. The economics are still uncertain, but the resources are real. Recent missions to asteroids, Bennu, NASA's OSIRIS-REx, and Ryugu, JAXA's Hayabusa 2, have returned samples to Earth. These samples contain pristine material from the early solar system: carbon, organic molecules, water-bearing minerals. They're time capsules from 4.5 billion years ago. NASA's Psyche mission, launching in 2023, will visit the asteroid 16 Psyche, a 140-mile diameter M-type asteroid that might be the exposed core of a protoplanet. If Psyche is indeed a planetary core, it'll give us a view of something we can never see on Earth, the interior of a differentiated planet. In 2022, NASA deliberately crashed a spacecraft into asteroid Dimorphos to test planetary defense techniques. The impact successfully changed Dimorphos's orbit, proving we can deflect asteroids if needed. This DART mission was humanity's first test of actively defending Earth from asteroid impacts. The asteroid belt is a graveyard of worlds that never formed, a collection of planetary building blocks that never quite made it. But it's also a laboratory for understanding planet formation, a potential source of resources, and a reminder that the solar system's formation was chaotic and violent. And speaking of chaotic and violent, we need to talk about the solar system's edges, the places where sunlight fades to almost nothing and the cold becomes absolute. But before we venture into that darkness, let's wrap up our journey through the most unusual worlds in our cosmic neighborhood. We've traveled nearly 3 billion miles, from sun-scorched Mercury to frozen Triton. We've seen volcanic hellscapes, subsurface oceans, methane lakes, metallic hydrogen planets, diamond rain, and geysers erupting on worlds colder than a deep freezer. And here's the thing, we've only scratched the surface. Beyond Neptune lie the dwarf planets of the Kuiper Belt Pluto, with its nitrogen ice plains and water ice mountains. Haumea shaped like a football and spinning so fast it should tear itself apart. Makemake with its mysterious lack of atmosphere, and Eris, larger than Pluto, at the edge of the solar system. New Horizons' 2015 flyby of Pluto revealed a geologically active world with glaciers of nitrogen ice, mountains of water ice, and a heart-shaped region called Tombaugh Regio. Pluto is so cold that water ice is as strong as granite, and nitrogen ice flows like glaciers. Yet the world is active possibly with a subsurface ocean, definitely with ongoing geological processes. At 3.6 billion miles from the Sun, where temperatures are minus 375 degrees Fahrenheit, Pluto is not dead. It's alive with geology driven by internal heat and exotic ice dynamics. Haumea is one of the weirdest objects in the solar system. It's shaped like an elongated ellipsoid, roughly 1,400 miles long and 600 miles wide, and it rotates once every 4 hours. That rapid rotation stretches Haumea into its football shape. If it spun any faster, it would fly apart. And Haumea has rings. A dwarf planet with rings, discovered through occultation observations in 2017. The Kuiper belt extends from Neptune's orbit out to about 50 astronomical units. Astronomical units, where 1 astronomical unit is Earth's distance from the Sun. Beyond that is the scattered disk, where objects have highly elliptical, tilted orbits. And beyond that is the hypothetical Oort cloud, a spherical shell of comets extending halfway to the nearest star. We've never directly observed the Oort cloud, but comet orbits suggest it exists. If you think of the solar system as Earth's orbit equals 1 inch, then Jupiter is 5 inches away, Neptune is 30 inches away, Pluto is 40 inches away, the Oort cloud is 50,000 inches away, nearly a mile. The solar system is mind-bogglingly vast, and we've explored only a tiny fraction of it. So what have we learned from our tour of the solar system's most unusual worlds? First lesson, Earth is the anomaly. We live on a geologically active, temperature-stable, water-rich, oxygen atmosphere world with a protective magnetic field. That combination is rare. Most worlds are either too hot or too cold, too large or too small, too geologically active or too dead, too hostile for anything we'd recognize as habitable. Earth isn't normal. Earth is the outlier. We won the cosmic lottery, and we should probably appreciate that more. Second lesson, the solar system is far more diverse than we ever imagined. Before spacecraft exploration, we assumed planets and moons would be fairly similar rocky balls or icy balls, cratered and dead. Instead, we found volcanoes erupting constantly for billions of years, subsurface oceans containing more water than Earth, atmospheres thicker than Earth's on tiny moons, storms lasting centuries, winds faster than sound, temperatures varying by 1,000 degrees between day and night, geysers erupting on worlds colder than liquid nitrogen rivers, and lakes made of natural gas, rings that shouldn't exist, magnetospheres more powerful than anything we imagined. Every mission to a new world has produced surprises. Every dead world turned out to be more interesting than expected. Third lesson, life might not be as rare as we thought. Europa, Enceladus, Titan, possibly Ceres' multiple worlds in our solar system, have the ingredients for life. Liquid water, organic molecules, energy sources, time. If life arose in even one of these places, independently from Earth, it would prove life isn't unique to our planet. It would suggest the universe is full of life, because if it happened twice in one solar system, it probably happens everywhere conditions are right. The question isn't, is there life elsewhere in the solar system? The question is, where will we find it first? And we're working on answering that question. Europa Clipper launches in 2024 to study Europa's ocean through multiple flybys. Dragonfly launches in 2027 to explore Titan by helicopter. Future missions to Enceladus are being planned. Concepts for submarines to explore Europa's subsurface ocean are in development. Within our lifetimes, we might discover life beyond Earth, not by traveling to other stars, but by exploring our own solar system. But with exploration comes responsibility. NASA and other space agencies follow planetary protection protocols to avoid contaminating other worlds with Earth life. If Europa has its own ecosystem, the last thing we want is to introduce Earth bacteria that could outcompete native European life. We're sterilizing spacecraft, planning careful sampling methods, and thinking seriously about how to explore without destroying what we're looking for. Fourth lesson, understanding other worlds helps us understand Earth. Venus shows us what happens when a greenhouse effect spirals out of control. Mars shows us what happens when a planet loses its magnetic field and atmosphere. Io shows us extreme volcanism. Titan shows us a prebiotic chemistry laboratory. Every world is a natural experiment in planetary processes. By studying them, we learn about Earth's past, present, and potential futures. Fifth lesson. We're just getting started. The spacecraft that explored these worlds, Voyager, Galileo, Cassini, New Horizons, were primitive by today's standards. Limited cameras, limited data transmission, limited instruments. Future spacecraft will be smarter, more capable, more resilient. AI-driven autonomous exploration, advanced mass spectrometers capable of detecting biosignatures, landers that can survive for years in extreme environments. We're re-entering a new era of planetary exploration, where we do and just fly past worlds. We land on them, rove across them, drill into them, and potentially even return samples. Could humans visit these worlds? The inner solar system, Mercury, Venus, Mars, is technically within reach, though only Mars is remotely survivable. The outer solar system? That's a different challenge. Jupiter's radiation would kill astronauts. Saturn is too far with current propulsion. The ice moons are even farther. But technologies like nuclear propulsion, better radiation shielding, and in situ resource utilization could make human missions to the outer solar system possible within this century. Imagine humans living in rotating habitats around Europa, sending submarines into the ocean below, or floating cities in Venus's upper atmosphere, or research stations on Titan studying prebiotic chemistry. It sounds like science fiction, but so did landing on the moon until we did it. Sixth lesson. The solar system is a system interconnected and dynamic. Jupiter's gravity shapes the asteroid belt. Io's volcanoes feed Jupiter's magnetosphere. Enceladus's geysers create Saturn's E-ring. The solar wind affects every atmosphere. Nothing exists in isolation. Every world influences and is influenced by its neighbors, creating a complex gravitational and electromagnetic dance that's been going on for 4.5 billion years. And finally, the most important lesson: perspective. Looking at these bizarre, extreme, alien worlds reminds us how special Earth is, but also how small. All of human history, every empire that rose and fell, every war fought, every discovery made happened on a tiny temperate rock orbiting an average star in an unremarkable galaxy. Meanwhile, just next door cosmically, there are worlds where the wind screams at supersonic speeds, where oceans hide beneath ice for billions of years, where it rains diamonds and methane, where volcanoes never stop erupting, where a single storm has raged for 4 centuries. Carl Sagan called Earth a pale blue dot, a mote of dust suspended in a sunbeam. He was right, but that pale blue dot is home. It's the only world we know for certain that harbors life. It's where everyone we love, everyone we've ever heard of, every human being who ever lived out their lives. And when we look at Earth from space, this blue marble swirled with white clouds, green continents, and deep oceans, we see something none of these other worlds have. A planet alive with biology, pulsing with ecosystems covered in the fingerprints of life. Earth is weird too. It's weird because it's alive. Which brings us to a sobering thought. We've seen what happens when planets lose their magnetospheres, when greenhouse effects spiral out of control, when atmospheres are stripped away by solar wind. These aren't hypothetical scenarios. They're documented histories of worlds in our own solar system. Earth is fragile. The conditions that make it habitable are a delicate balance that could, theoretically, be disrupted. Venus was probably habitable once. Now it's hell. Mars had rivers and possibly oceans. Now it's a frozen desert. Earth is still in the Goldilocks zone, but we're learning that Goldilocks zones aren't permanent. Planets evolve. Climates change. Atmospheres can be lost. This is why exploring and understanding other worlds matters. It's not just about curiosity or discovery. It's about survival. Understanding how Venus turned into a hothouse and Mars into a freezer helps us understand the boundaries of habitability. It helps us recognize the warning signs. It helps us protect the only habitable world we currently have. The next few decades will be golden age of planetary exploration. We'll land on Europa. We'll fly through Titan's atmosphere. We'll sample the geysers of Enceladus. We'll study Venus with dedicated missions. We'll return samples from Mars. And with each mission, we'll answer questions and raise new ones. Does life exist in Europa's ocean? How deep are Enceladus's hydrothermal vents? What prebiotic molecules exist in Titan's lakes? Could humans build habitats on Mars? And here is the really exciting part. Every weird world we study in our solar system helps us understand the thousands of exoplanets we're rediscovering around other stars. Hot Jupiters orbiting closer to their stars than Mercury? We can use Jupiter as a template. Super Earths with thick atmospheres? Venus and Titan provide clues. Ocean worlds? Europa and Enceladus show us what to look for. Our solar system is a Rosetta Stone for deciphering alien worlds. The big questions remain. Are we alone in the solar system? Almost certainly not, if you include microbial life. Are we alone in the universe? Given the sheer number of potentially habitable worlds, probably not. Will we find life in our lifetimes? Maybe. Europa Clipper and Dragonfly could detect biosignatures within the next 2 decades. Will humans become a multiplanetary species? Depends on whether we survive long enough and develop the technology. Imagine for a moment being the first human to stand on Europa's ice, to drill through and send a camera into the ocean below, to see for the first time an alien ecosystem that evolved completely independently from Earth. Or imagine being the first human to float through Titan's atmosphere, looking down at methane lakes and organic dunes, knowing you're standing on a world that might be showing us what Earth looked like before life arose. These aren't fantasies. These are possible futures, if we choose to pursue them. Our journey through the solar system as most unusual worlds has taken us from volcanic hell to frozen water worlds, from atmospheric giants to tiny rubble pile asteroids, from the scorching surface of Mercury to the frigid geysers of Triton. We've seen worlds that challenge our assumptions, that expand our imaginations, that remind us that the universe is far stranger and more wonderful than we ever anticipated. But every journey ends where it began, home. We've explored the bizarre worlds of the solar system, but the most remarkable world remains the one beneath our feet. Earth with its oxygen atmosphere, liquid water oceans, protective magnetic field, and thriving biosphere is the true oddity, the exception, the anomaly. And someday, maybe some kid watching this video will be the one to land on Europa, or fly through Titan's atmosphere, or discover life in Enceladus's ocean. Because the solar system isn't finished being explored, we've barely started. The universe is vast, strange, and full of wonders. And we're lucky enough to live in a time when we can actually go and see them. So keep looking up, keep asking questions, keep exploring. Because out there, orbiting our sun, are worlds weirder than any science fiction. And they're real, they're waiting, and they're ours to discover. Welcome to the solar system. It's stranger than you think, and more wonderful than you can imagine.